Welcome to lesson 36. So in lesson 35, we calculated a confidence interval for a proportion from one population. Now we're going to look at doing a hypothesis test. So just a caution, the conditions are going to be a tiny bit different here. And this will be the first time really that we have introduced conditions that are different for the hypothesis test versus the confidence interval. So this is not when I want to test the average value. I want to test a proportion. Beware, copy and paste the proportion P from a single population. So pretty much always you're going to want a representative sample. Most of the time you're going to do this by taking a random sample. It is possible to take it, get a representative sample without random, but it usually takes some justification. It's harder. Condition 2, though, it has changed just a little bit, but enough that it will be very different. So we want to know that we took a big enough sample that the central limit theorem is going to kick in. But specifically, I want to know that if I'm testing a claimed value P naught, that the sample size times that P naught, that's going to be at least 10. So if the null is true, and I took the sample size I took, would I have expected to take at least 10 successes? And if the null is true and I took my sample size, would I have expected at least 10 failures if the null is true? And that is the change. It's not based on what I saw in my sample. It's now based on if the null were true and I took the sample size I took, would the sample size have been big enough given what we expect to happen? So similar to before, you can have a one-sided, lower one-sided, so maybe you're interested in, hey, is the proportion of that population that has this characteristic less than a certain value? You can look at upper one-sided, or you can look at two-sided, like, hey, is it different? So our test statistic, we're going to have a z-test statistic. Anytime pretty much we're messing with proportions, we're going to be looking at a z statistic. So it's going to be similar in structure where what we saw in the sample, so P hat, minus what's claimed, P naught, over a standard error, so a measure of spread. But notice the standard error here changes for a hypothesis test and a test statistic. So when we do hypothesis testing, we assume by default that this is true, that P is equal to P naught. So that is what we plug into the bottom for P. We plug in P naught. Whatever that value is, whatever is claimed, that's what we put in the denominator. So as far as the only real sample information, we're going to have the sample size and the sample proportion. That's the only time any sample information will show up. The rest is pretty much going to all be whatever is claimed. So because we really, really love these coffee cups, we're going to stick with this coffee cup example. So there's this manufacturer, they make coffee cups. They're concerned that, they probably don't want more than a certain proportion of them to be defective. If so, most manufacturers will shut down and troubleshoot, maybe fix a machine. So here, they say, hey, if we find that it's greater than 0.09, so if more than 9% of the cups in this batch are defective, the manufacturer is going to stop and investigate the process. So we want to test the proportion, and they go ahead, they take a random sample of 200 cups, and 20 of them are defective. So this is the same, like P hat is equal to 28 out of 200 is 0.14. Same sample information as last time. So stating my question, if it's a hypothesis test, it's going to be stated in a way that's like it's a yes or no question. So is the proportion of all coffee cups manufactured in this large batch by this manufacturer, is the proportion that are defective higher than 0.09? Higher than 0.09 because that's what they were interested in. If it's higher than 0.09, they're going to stop the process and investigate. So my parameter of interest, it's nested in here, the proportion of all coffee cups that are defective. So fill that in. And remember, parameters never ever are going to have a hat or a bar. So it's just going to be P. So my population proportion, P, is the proportion of all coffee cups manufactured in this large batch that are defective. My significance level, so in general, I'm just gonna, if we don't give you one, the good default is going to be alpha equal to 0.05. That's going to be the norm here. Often though, if you have a confidence interval and like a 90% and you do 0.10, that would be a typical thing to do as well. We're not going to be too picky. I honestly picked 0.05 on purpose, so we'll see. Oh, my inventory. I didn't put my inventory. So P hat is going to be 28 over 200 is 0.14. My sample size is 200. Different from my inventory before, P naught is going to be 0.09 because this is the claimed value we're interested in comparing. So note, this 0.09 value, it didn't come from the sample. It came from somewhere outside. The manufacturer said, hey, if it's higher than this amount, we're going to stop things. So P naught, 0.09. So my hypotheses here. So remember, I'm going to always have P. I'm always going to have an equal sign in my null hypothesis here. And then the claimed value, 0.09. For proportions, there are no units, so I don't need to worry there. For my alternative, I'm still going to have P. I'm still going to have 0.09. But this is going to refer back to the question, oh, is it greater than 0.09? That's what I'm interested in finding out. So looking at my conditions for inference, random representative sample, yes, because I took a random sample of 200 from the large batch. I'm not sure how many are in a large batch, but it must be pretty large. And then these conditions, the size conditions have changed from before. So now I want to know if the null is true and 9% really are defective. Could I have expected to take a sample of 200 and see at least 10 defective and 10 not defective? Short answer, yeah. Yeah, I could have. So 9% of 200, it's going to be 18. That's bigger than 10, yes. So if I expected to see 18 defective, I would have expected to see 200 minus 18 that aren't defective. So, math, 181, maybe. No. 2. I can add sometimes. That's also at least 10. So if the null were true and 9% really were defective and I took 200, I would have expected around 18 to be defective and around 182 to not be defective. Both of those values are above 10, so I'm good. And then somewhere, my, yeah, I think I wrote on the last one, my significance level. Okay, cool. So then calculate the test statistic and p-value. This is a big part of why we're like, hey, take the inventory, because now we have to plug everything in. So remember that p naught was equal to 0.09, p hat is equal to 0.14, and then my sample size was 200. So now I have everything I need. And so whenever you calculate a z-test statistic, this means you can use the z-table to find your p-value. Things to note, if the null were true, and it really is 0.09, what we observed was 0.14. So this is p hat right here. So I will be looking for this upper tail probability. So let's find the z-statistic first. So 0.14 minus 0.09 over, so 0.09 times 1 minus 0.09 over 200, square root all that. This is not do in your head math unless you're just really good that way. I end up getting positive 2.4 So I can break that up into 2.4 and 0.07. So 2.4 tells me which row to look at, 0.07 tells me which column. So so this means if I had 2.47 here, the area here on the left, 9932. The reason I was fussing about this was saying, hey, my alternative says greater than, so I need to look at greater than. So I actually want this yellow area. My p-value, my one-side p-value will be that yellow area. So 1 minus 0.9932, 0.0068. So my one-sided p-value, do I have room here? My one-sided p-value is 0.0068. And one thing to keep in mind is then you need to remind yourself, hey, the alternative, is it one-sided or two-sided? So my alternative was that p was greater than 0.09. This is one-sided, so I'm done. I do not need to multiply my one-sided p-value by 2. I don't need a two-sided p-value. So we have a z statistic of 2.47 at the 0.05 significance level. So looking at this p-value, 0.0068, it's less than 1%. It's pretty small. So our p-values, if you watch the song, we like our p-values low, right? Yeah, I'm sorry, I'm just not singing right here, right now. It'd be horrible. We can reject the null if our p-value is really small. If our p-value is smaller than the significance level, we can reject it. So we reject the null hypothesis at the 0.05 significance level with a z-statistic at 2.47, a one-sided p-value of 0.0068. So then here, this is where we look at that scale, like, oh, how strong is my evidence? You could say very strong or convincing. Either one would be okay here. Evidence that the proportion of, so now you have to put the population. So all cups manufactured in this batch. You could put in this large batch, that would be fine. That what? Oh, that are defective. Is, and then this is going to be the alternative in context. So we were looking at greater than 0.09. So is greater than 0.09. So we have very strong evidence the proportion of all cups manufactured in this large batch that are defective is greater than 0.09. What this translates to, they need to shut it down. They need to shut down this process and investigate, because they said if it was higher than 0.09 that they would stop. So that's where we are with that particular problem there. So then I believe we have a couple examples here. So given the following information, calculate the z-test statistic and p-value. This is a great moment to press pause, give it a try. It is way better than just watching me give you an answer. Give you all a second. Okay, so right off the bat, it says calculate the z-statistic and p-value. So we're looking at, it's a two-sided test because of this not equal sign. It's for a proportion. That immediately tells us not a t-statistic. So not only that, it's if the null were true. So if it were true, that means that p is equal to 0.5, right? And then what we actually observed, so p hat is going to be equal to 59 over 100. That's going to be 0.59. That's pretty nice. So I saw 0.59. So you're going to look, your one-tail p-value will be whatever area is above 0.59. Your two-tail, so 0.09, 0.09, you get 0.41, anything below 4.1. That ends up, the area corresponding with those two tails, that ends up being our two-sided p-value. Basically what it translates to is anything 0.09 or further away from 0.05 is as or more extreme than what we saw in our sample, because we saw 0.59. What's claimed is 0.5. So 0.09 or further away from 0.5, all of that is as or more extreme than what we saw in the sample. So here, go ahead, our z statistic, p naught is equal to 0.5, going to be p hat minus p naught over p naught minus p naught. Oh yeah, I love having the squared down there. Over my sample. Ooh, that's so nice. Squares. That's not a coincidence at all. So what I saw in my sample, 0.59, minus what's claimed, 0.5, over 0.5 times 0.5 over 100. This is what I was talking about, like, hey, look at all the squares. It's so nice. You should get 1.8 given away here. So things to note is this area here, this ends up being 0.036, but that's only one side. This is also 0.036. We want a two-sided p-value. It ends up being d. This is the scenario where you forget to subtract from 1, and you also forget to multiply by 2. Note, if you ever try to multiply your one-sided p-value by 2 and you get over 1, that means something went wrong. You will never multiply your true like one-sided p-value by 2 and go over 1. It usually means that you took the wrong side probability. So then another example here, we have two different university industrial engineering programs. They want to go ahead, so two programs at two different universities, that's what they're talking about. The number of students, or proportion of students that pass the FE exam the first time they take it. So University 1's program, they have this many students take it, and this proportion of them pass the first time. University 2 has this many students, and this many of them pass the first time. That's the idea. So yeah, University 1, 26 students take it, 19 pass on the first try. University 2, 31 students take it, 14 of them pass on their first try. We want to know, is there a significant difference? So here we are looking at two populations, right? The assumption is that we don't have students that are in both programs. They're only in one at a time. And then we would need to look at what we're collecting. We're looking at proportions here, right? So student 1, did they pass or not pass? Student 2, did they pass or not pass? This is a categorical variable, which means we're looking at proportions. We are not looking at means, so we don't want ANOVA and we don't want a t-test. So this is actually none of the above. This is going to be a two-sample z-test for a difference in proportions. Which, hey, what do you think is coming up next, right? So technically we're going to do the confidence interval first, and then we'll get to the z-test. But yeah, that's coming up next. So it shouldn't have looked familiar yet, but that's where we are. So we're going to start looking at, so this was looking at one proportion for one population. Now we're going to look at comparing a proportion across two groups or two populations. That's what's next in lesson 37. So we'll see you there.